I'd like now to talk about the synthetic utility of the diazotization process. The implication is that if we start off with a bare benzene ring, we can pretty much add any of these X groups that I talked about in the previous mini lecture. And the way we would do that is to first of all nitrate the ring using HNO3 and H2SO4. That'll put an NO2 on the ring. We've talked about that reaction already. But the other reactions we haven't talked about yet are that we can take the nitrobenzene and we can reduce it using hydrogen over palladium. It's hydrogen gas over palladium metal, and what that will do is reduce the NO2 to aniline or NH2. We can then take that aniline and convert it into the diazotized group by using HNO2, or if you like NaNO2 and HCl, but it has to be at 0 degrees. Both of these are the same thing. And then we can take that diazonium salt and we can hit it with any of these X's that I talked about in the previous mini lecture, the CUX, HBF4, H2O, H3PO2, or Ki, to give us the desired compound that we want. Alright, let me show you a couple of examples. Alright, so we can go from benzene to a fluorobenzene. In fact, this is really the only way that you can put a fluorine on an aromatic ring. There aren't very many useful processes that do that, except for this one. So what we do is we treat this with HNO3 and H2SO4, and that gives us the nitrobenzene compound. Then I can treat that with hydrogen over palladium, which gives me aniline. This aniline can be treated with NaNO2, HCl at 0 degrees, and that will give us our diazonium salt. And you can include the Cl as Cl minus as the counter ion if you want to, or just leave it as N2 plus. And then we just need to choose the reagent that we'll put an F on, and the one that will do that will be HBF4 and heat. And that will give us our final product, which has the fluorine connected in place of the N2 plus. Alright, so that's for that one. Now we can also take advantage of directing effects of other stuff that's already on the ring as well. And we'll show that in the next example, where we're starting off with benzoic acid, and we want to put a CN group meta to the benzoic acid. Alright, so what we'll do is we start off with the benzoic acid, and we're fortunate in that benzoic acid is a deactivating group. So we've got a C double bond O here that's going to have a delta minus on the O and a delta plus on the C, which means we're going to be sucking electrons out of the ring, which means it's going to be a meta director, and that's going to allow us to put a group down here. So our first step will be to nitrate, just as it was before, HNO3, H2SO4. And that puts an NO2 group in the meta position to the carboxylic acid group. Alright, so now we can go ahead and reduce the nitro group to an aniline, and we do that using hydrogen palladium. Then we treat that with NaNO2 and HCl at 0 degrees Celsius, which gives us our diazonium salt. And now we need to choose the reagent that will allow us to put a CN here in place of that, and that would be CuCN. So copper 1 cyanide, and that puts a CN in that position. Alright, so even though it looks a little different from what I wanted, it's just the same thing, it's just been rotated around a little bit, and that would be the synthetic process that you'd use. I want to do one more example, and this actually makes use of a reaction we haven't talked about yet, but we will talk about in a mini lecture in the near future. And I just want to bring about this this example just to show you the manipulation of directing effects. Alright, so let's say we started off with something like this. Now, we're going to start with toluene, and we want to end up with, as a product, we'll put an I here, this one. Alright, so what we're going to do is we're going to have to look at take a serious look at the directing effects of the methyl group here. Now, one thing we know we can't do is we can't take this with the methyl group and nitrate it, because if we nitrate this, we're going to end up with ortho and para products. That's because the methyl group is an activating group, so we'll have CH3, we'll end up with the NO2 here, and we'll end up with the NO2 in the para position. Alright, so as you can see, that's not going to be a desirable situation, because then when we try and reduce these, we're going to end up with something where we don't end up with the kind of regiochemistry that we need. That is, we want meta, we don't want ortho and para products. Alright, so let's talk about how we can obtain the products that we need by manipulating the directing effects of our groups. Alright, so we're after the iodine here in the meta position. So what we've got to do is somehow find a way to convert this CH3 to the carboxylic acid first, and then we can do our synthesis from there, knowing that this will be meta directing. So the reaction we haven't talked about yet is this one, where we can take this compound and add KMNO4, which is a very good oxidizing agent, and the product will be what we need, which is benzoic acid. So if we do that, we now end up with something that is actually a meta director. Now we can go ahead and continue with our synthesis. We can treat that with HNO3 and H2SO4, which will nitrate it, and as we said before, we know it's going to nitrate it in the meta position to the acid group. And now we can go ahead and reduce that. We can now treat that with NaNO2 and HCl at 0 degrees C, and that will diazotize it. Now we want an iodine down here at the bottom. So what we'll do is we'll choose the reagent that will produce an iodine, that's Ki. And that will put the iodine in the meta position to the carboxylic acid group. And that gives us our product. Right, there we go.